testing quantum theory in curved spacetime. For over a century, quantum theory has dazzled us with its ability to explain the tiniest building blocks of the universe. Yet there's one glaring issue that continues to stump even the brightest minds. How does the discrete, chunky nature of quantum particles align with the smooth, continuous fabric of spacetime? This profound mismatch is not just an academic curiosity, it strikes at the heart of some of the most fundamental questions in physics. Does spacetime itself have a granular structure? And if it does, could he ever detect it or see its effects ripple through the universe? Now, a bold new proposal by Jacob Covey and his team at the University of Illinois, Urbana-Champaign might bring us closer to answering these mysteries. Their idea hinges on using advanced quantum tools to explore the interplay between quantum mechanics and Einstein's general relativity within Earth's gravitational field, a realm where space-time curves due to gravity. But here's where it gets controversial. While many physicists agree that merging quantum theory with gravity is essential, others argue that this entire pursuit may be misguided. Should gravity even be quantized? Or are we chasing a phantom? Regardless of where you stand, the experimental approach suggested by Covey and his colleagues represents a significant leap forward in testing these ideas empirically. What makes their proposal particularly intriguing is its focus on quantum gravity, one of the biggest unsolved puzzles in modern science. Theories like string theory and loop quantum gravity have long dominated discussions about how to unify quantum mechanics and gravity. However, these remain largely theoretical, relying on mathematical models rather than concrete evidence. Historically, experiments to test quantum gravity were considered impractical. But recent advances in quantum optics, gravitational interferometry, and astronomical observations have opened up exciting possibilities. Covey's team suggests constructing a highly sensitive quantum system that spans vast distances across the Earth's surface. Imagine splitting a single atomic clock into 3 parts and placing them at different elevations, kilometers apart. By encoding the presence or absence of the clock into each part, they create a shared entangled quantum state. This setup allows researchers to measure tiny differences in what's called Proctor time, the time experienced by objects in curved spacetime across these locations. These measurements could reveal whether spacetime behaves as expected under extreme conditions. And this is the part most people miss. Beyond probing spacetime curvature, the experiment could also test foundational aspects of quantum theory itself. For instance, it could examine whether the rules governing quantum states, like linearity, unitarity, and probability calculations via the Born rule, still hold true when gravity enters the picture. Such insights would deepen our understanding of both quantum mechanics and spacetime, potentially uncovering phenomena that defy current theories. Of course, executing this ambitious plan won't be easy. Creating and maintaining such a delicate, entangled quantum state over large distances presents enormous technical challenges. Similar hurdles face other cutting-edge efforts to detect quantum gravity signatures, from gravitationally induced entanglement to exotic interference patterns in gravitational fields. Moreover, the Born rule, the cornerstone of quantum probability, hasn't been rigorously tested in gravitational contexts, making it fertile ground for surprises. So what's next for quantum gravity research? While implementing Covey's proposal pushes the boundaries of current technology, the potential rewards are immense. Whether confirming existing theories or revealing entirely new physics, experiments like these will undoubtedly shape the future of quantum science and technology. But let's pose a thought-provoking question. If quantum gravity turns out to behave differently than anticipated, how should we rethink our understanding of reality itself? Share your thoughts in the comments below. Exploring the quantum internet and Einstein's gravity, a new frontier. Imagine a world where the deepest mysteries of the universe are unlocked not just by theoretical physics, but by actual experiments. This isn't just a dream, it's becoming a reality with the latest developments in quantum networks. These networks, which are rapidly spreading across the globe, are not only paving the way for a highly secure worldwide quantum internet, but are also opening new avenues to explore fundamental questions about the universe. But here's where it gets controversial. What if our understanding of quantum mechanics changes in the presence of gravity? Quantum networks, traditionally seen as the backbone for secure global communication and linking distant quantum computers, are now proving to be crucial in examining the relationship between quantum mechanics and the curvature of space-time. This groundbreaking approach was recently highlighted in a study led by Igor Pikovsky from Stevens Institute of Technology, along with Jacob Covey at the University of Illinois at Urbana-Champaign and Johannes Beauregard at Harvard University. Their research, detailed in PRX Quantum, introduces the first experimental method to investigate how the bending of space and time affects quantum mechanics. Einstein's theory of general relativity tells us that gravity is not a mere force, but the result of space-time curvature. This concept has been verified with incredible accuracy and has even permeated popular culture, as seen in movies like Interstellar. But the intriguing part, and often misunderstood, is how this curvature impacts the quantum world. Does the quantum realm behave differently in curved spacetime? Could this necessitate a revision of quantum theory, general relativity, or both? Pikovsky and his colleagues have embarked on a novel experimental journey using quantum networks. Their previous work, published in Physical Review Research, laid the groundwork for this exploration. They demonstrated that quantum networks could uniquely test the simultaneous effects of quantum superpositions and gravitational time dilation. In simpler terms, quantum networks allow atomic clocks to operate in superpositions, where they experience different rates of time flow simultaneously due to the curvature near Earth. This capability of quantum networks to probe the interplay between quantum mechanics and gravity is not just academic thrilling, it's a potential game changer in physics. Pikovsky himself notes, the interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating. Quantum networks will help us test this interplay for the first time in actual experiments. The team's recent protocol involves distributing quantum effects across network nodes using entangled W states and recording the interference between these systems. By leveraging advanced quantum technologies like quantum teleportation and entangled Bell pairs, they aim to conduct a real-world test of quantum theory in curved spacetime. This research suggests that quantum networks could be more than just a tool for building a future quantum internet. They might also provide a unique platform for testing fundamental physics in ways that classical methods cannot match. Pikovsky's bold statement, "We assume that quantum theory holds everywhere, but we really don't know if this is true," challenges us to rethink the role of quantum networks. Could it be that gravity alters how quantum mechanics operates? As we delve deeper into these questions, the implications could be profound, potentially leading to new theories or modifications of existing ones. What do you think? Could the integration of quantum networks and gravitational theory lead to revolutionary changes in our understanding of the universe? Share your thoughts and join the discussion below. This quantum clock experiment could break physics as we know it. What if the very fabric of reality could be unraveled by a clock no bigger than a grain of sand? A groundbreaking experiment is poised to challenge the foundations of physics by merging two of its most perplexing theories, quantum mechanics and Einstein's gravity. Scientists from the University of Illinois, Harvard, and other institutions are proposing a test that could either confirm our current understanding of the universe or shatter it entirely. But here's where it gets controversial. What if gravity doesn't just warp space and time, but also reshapes the rules of quantum behavior? And this is the part most people miss. This experiment isn't just about timekeeping. It's about asking whether the strange, probabilistic nature of quantum systems can survive in a world where gravity bends everything, including the passage of time itself. At the heart of this proposal are 3 atomic clocks, each smaller than a speck of dust, suspended at varying heights. These aren't ordinary clocks. They're quantum devices that exist in multiple states simultaneously, connected through a phenomenon Einstein called spooky action at a distance. By entangling these clocks and spreading them across elevation differences of about a kilometer, researchers train to observe how gravity's pull affects their synchronized ticking. The goal? To detect whether the rules of quantum mechanics, like the Born rule, which governs probabilities in quantum measurements, or the principle of unitarity, which ensures probabilities add up to 100%, hold up when gravity is the dominant force. The experiment hinges on gravitational time dilation, a well-documented effect where clocks in stronger gravitational fields tick slow. For example, GPS satellites must account for this difference to stay accurate. But here, the stakes are higher. The team plans to use ytterbium-171 atoms trapped in optical cavities and entangled into a W stake where information is shared across all 3 locations. Imagine 3 clocks, each experiencing time differently due to their altitude, yet instantaneously influencing one another. The result? A way to measure how gravity's curvature affects quantum interference patterns, a test that's never been done before. This setup is designed to tackle 3 pillars of quantum theory: linearity, where the quantum equations behave predictably; unitarity, where the probabilities remain consistent; and the Born rule, how measurements translate to outcomes. But what if gravity disrupts these principles? For instance, quantum interference usually follows strict mathematical rules when multiple paths are involved. Could gravity introduce new unaccounted for interference? The researchers suggest using superatoms, clusters of up to 100 entangled atoms, to amplify signals and detect these effects within seconds rather than minutes. This clever trick could make the experiment feasible with current technology, though challenges remain. Technical hurdles include maintaining quantum coherence, the fragile state that allows quantum effects, for up to 50 seconds per atom. Current atomic clocks achieve around 30 seconds, so improvements in stability and noise reduction are critical. Environmental factors like vibrations from nearby buildings or temperature fluctuations could also muddle results. One station would need to be placed at a significant elevation, requiring precise engineering to isolate it from disturbances. And while the GHZ superatom approach offers a theoretical boost, entangling 100 atoms with the required fidelity has never been demonstrated. The implications stretch far beyond Earth. If successful, this experiment could pave the way for studying extreme gravitational environments, black holes, neutron stars, or even the early universe, using quantum networks of satellites. It might also bridge the gap between quantum mechanics and general relativity, two theories that currently clash at the deepest levels. But here's the twist. If the results deviate from predictions, it could mean a total rewrite of physics. Are we ready to accept that reality behaves differently when gravity is involved? Or will this test reaffirm the consistency of our quantum world? The answers could redefine how we perceive time, space, and everything in between. So what's your take? Do you think gravity will bend quantum rules, or will the universe stick to its script? Share your thoughts in the comments. This is the kind of question that keeps physicists and curious minds awake at night. After all, the next breakthrough in understanding reality might just come from a clock the size of a grain of sand.